We already know how to determine the charge carrier's concentration in a semiconductor in different situations. You have also learned how electron-hole pairs are generated in a semiconductor absorber that form an active part of solar cells. The next step is to separate the electrons from the holes. To understand how that works, you first need to know how the charge carriers move around in a semiconductor and cause an electric current. Before we look at the different transport mechanisms, let's briefly recap what we mean by electric current. In a simple circuit like this, we define current as the movement of charge carriers, and the direction of current is determined by the flow of positive charge. If electrons that carry negative charge are flowing in certain direction, the direction of current is defined to be in the opposite direction. This means that electric current is in opposite direction as the flow of electrons. And electric current is in the same direction as the flow of holes that carry positive charge. This is important to remember so that we can later easily understand electric current caused by different charge carrier transport mechanisms. We will discuss the movements of both electrons and holes in this video. However, to keep things consistent, we will use the word current to describe flows of both carriers. Furthermore, you will notice in this video that we shall use the letter J rather than I to describe the results of charge transport. This is because when dealing with solar cells, we are interested in current density, which is the current per unit area, rather than just the current. As an example, we can use the flow of carriers from left to right on the slide. If we have electrons moving from left to right due to a given mechanism, we will state that the current caused by electrons, I electrons, is moving from right to left. On the other hand, if we have holes moving from left to right, we will say that the current caused by holes, I holes, is moving from left to right. So just to keep in mind that when we have I or J with a subscript such as electron or hole, we do not mean the flow of that particular charge carrier. We always mean the flow of positive charge due to the movement of those carriers. I will always be opposite the movement of electrons and will go in the same direction as the flow of holes. To begin the discussion regarding the motion of charges, let's start with the simple case of a system in equilibrium. In equilibrium, charges are spread all over the solid and their density is ideally constant as a function of position. This means that there is no driving force for these carriers to move in the lattice in a certain direction. As a result, no net current flows. However, with the solar cells, we need to understand how semiconductors work when they are not in equilibrium. Let's look at some of the mechanisms behind the individual charge carrier transport in semiconductors. First, we have to consider thermal motion. Electrons are able to move as a result of thermal excitation. However, this movement is random and equal throughout the whole semiconductor. Once a semiconductor reaches a thermal equilibrium, we are not able to observe a net charge transport even though individual charges are moving due to the thermal motion. Since current is the result of a net transport of electrons, random motion is not of interest for photovoltaic applications. On the other hand, let us look at two different forms of transport which are important to solar cells. Two main mechanisms of carrier transport in solar cells are drift and diffusion. Drift is driven by an electric field. Diffusion is based on a thermal motion and driven by a concentration gradient of charge carriers. Let's begin with drift. Drift is the term used for charge transport that results from the interaction between the charged particles and an electric field. Here we see some electrons in a material. If an electric field is present, electrons will move in the direction opposite to it. On the contrary, positive particles like holes will move in the same direction of the field. We can observe that unlike random thermal motion, a net current flow is present. Because electrons carry negative charge, their drift in the direction opposite to the electric field results in a current density, Jn drift, that actually points with the electric field. Holes drift with the electric field, giving rise to a hole drift current density, Jp drift, that also points with the field. So, even though electrons and holes move in opposite directions, their associated current densities point in the same direction. Let's take a look at how to calculate these drift current densities. We will start with electrons. You can see the equations for the electron drift current density, Jn drift. It contains Q, the elementary charge, N, the concentration of electrons, and the electric field. The final term here, mu n, is the mobility of electrons. Let's take a closer look at mobility, an important semiconductor parameter. The mobility of a charged particle is defined as its ability to move through a medium in response to an electric field. It can be determined as the ratio between the average so-called drift velocity of the particle and the magnitude of the electric field. The drift velocity is temperature dependent. And it is important to remember that even though electrons and holes are generated within the same semiconductor, their mobilities are considerably different. The mobility values for electrons and holes for crystalline silicon at room temperature are given here. You can note that the mobility of electrons at room temperature is 3 times higher than that of holes. This means that under the same electric field conditions, electrons will move faster through the silicon material than holes. Mobility in a semiconductor can be impeded by collisions or scattering events of charged particles while they are moving through the material. There are 2 main types of scattering events to consider. The first is phonon scattering. Phonons are related to lattice vibrations. These vibrations increase with the increase in thermal energy. Therefore, mobility is inversely proportional to temperature. It is also important to take ionized impurities into account. The ionized impurities cause local electric fields that interact with moving charged particles, and the higher concentration of ionized impurities results in more interactions that lower the mobility. The increase in temperature raises the thermal motion velocities of charge carriers, which in turn can move faster across the local areas influenced by the ionized impurities. So in this case, mobility increases with increasing temperature. These 2 effects, temperature and the dopant concentration, are in competition, and we will now look at their net effect. Here, the mobility of electrons and holes in crystalline silicon are plotted as function of temperature with different dopant concentration. Overall, we can observe that the mobility decreases with temperature. Therefore, the dependence on phonon scattering dominates completely. However, as the doping increases, you can clearly see that the mobility becomes lower and the temperature dependence is less significant. Now that we have understood what mobility is and how it is influenced, let's go back to our drift equation. We see that the drift current of electrons depends on the mobility of electrons, electric field, and the concentration of charge carriers. The same equation holds for holes. The notable difference is that the hole current density depends on the concentration of holes and the hole mobility. With a quick analysis of physical units, we confirm that both the Jn drift and the Jp drift are quantified in femtoamperes per square centimeters. Summing up the proportionality factors between the current densities and the electric field, we determine the electrical conductivity of the semiconductor sigma, which is typically measured in 1/milliohms per centimeter. So how do we recognize drift transport in a Venn diagram? We know that drift takes place in a region with an electric field. In a Venn diagram, regions where the electric field is present are easily recognized. These are regions where the edges of the conduction and the valence bands have a slope. So remember, when you see a slope in a Venn diagram, you know that electrons and holes are affected by the electric field present in these regions. You can visualize the electrons as ball rolling down the slope and the holes as the helium-filled balloons that rise up and follow the slope. Here we see a band diagram where the direction of electric field goes from the right-hand side to the left-hand side. Note that the drift current densities result in currents that flow with the direction of field due to both electron and hole transport. Now, after we have discussed the drift transport, we will look at the other important transport mechanism, which is diffusion. Diffusion is a process in which particles move from regions of high concentration to regions of low concentration. You can imagine this is like dissolving some salt into water. To visualize this process, we start with a semiconductor with a large concentration of electrons on the right-hand side and no electrons on the left-hand side. This big concentration gradient will cause a large flow of electrons from left to right. The net flow of electrons in one direction will result in their diffusion towards the left side. However, gradually the concentration gradient will get smaller and smaller. This means that the net flow of particles will gradually decrease. Finally, we will arrive at an equilibrium state in which particles are uniformly spread all over the semiconductor. Now, when there is no difference in concentration and consequently no net flow of particles in a certain direction, the diffusion and the corresponding diffusion current will be zero. How can we calculate this current? Let's start analyzing the holes this time. The hole diffusion current density is proportional to the concentration gradient of holes, dP over dx. You can notice that the current is negative with respect to the gradient dP over dx. This makes sense because the holes flow from high concentration to low concentration. That is, opposite to the derivative of concentration, dP over dx. The elementary charge Q is also used here to convert the hole flux to electric current. Finally, you see the term dP, or diffusion coefficient for holes. You can see that the diffusion coefficient depends on temperature and the hole mobility along with constants Kb and Q that you should by now be familiar with. A similar equation is used for the diffusion current density of electrons. You may notice that there is no negative sign in the equation. Even though electrons do indeed flow opposite to the concentration gradient, dN over dx, they carry out negative charge. So two negative charge signs cancel each other out, and the resulting electron current density direction is in the same direction as the gradient dN over dx. With the introduction of the diffusion coefficient, we note that the ratio between the diffusion coefficient and the mobility is proportional to the temperature. This is the so-called Einstein relation and holds true for both electrons and holes. Also in this case, as in the case of drift components of current density, we confirm that both JP_diff and JN_diff are quantified in femtoamperes per square centimeters, while the diffusion coefficient is measured in centimeters squared per second. This ends the video on charge carrier transport. You learned about the two important transport mechanisms, drift and diffusion. Furthermore, you were introduced to the concept of mobility. This is the last video of this week and the introduction to semiconductor properties. Next week, you will learn about the generation and the recombination processes of charge carriers in a semiconductor.